Welcome back to one of Mr. Francois's famously friendly physics videos. Today we're going to be taking you through just a quick little intro and run through of vectors. So, what is a vector? Well, to talk about vectors, we really need to talk about something else first. We need to talk about a scalar. And now, okay, well, what's a scalar then, Mr. Francois? Well, I'll tell you. It's a scalar quantity which is described by a single number including units that indicates size or magnitude. Magnitude not necessarily meaning anything other than the amount or strength of something. So what's some examples of this? So temperature, we measure that in Celsius or Fahrenheit. Time, we measure in seconds. Mass, each of these has values which are used to just tell how much or how what the strength of it is. So that's a scalar. Then what's a vector? Well, a vector is a quantity that has both a direction and a magnitude, and it's represented by an arrow. So what's an example of this? Well, our classic examples are velocity, acceleration, or displacement. Each of these has a value, such as with velocity, it's how fast are you going, which is 30 miles per hour or 10 meters per second, whatever it may be. But it also has to have a direction associated with it, and that's what makes these things complicated. So it's 30 miles per hour going north, 10 meters per second going to the right. Whichever your directional association is for that problem, whether it's north, south, east, west, up, down, left, right, uh, which corkscrew or non-corkscrew, whatever it is, you have to have a direction component to it. And by having this direction component, it makes things not as simple. When you travel 30 meters north and then 20 meters south, you can't just add 30 to 20, even though that you have traveled a total of 50 meters. The displacement of that, where you end up, is only 10 meters away. So you can combine things together. But you have to do it in a very specific way. So let's take a look at how to resolve vectors. So we're going to run through a little practice problem here. So we're going to combine the following two vectors to find a resultant displacement. This is going to be one of the more difficult ones that you would have to do with 2D vectors. First one that we're going to use is 5 meters at 53.13 degrees. And the second, and that looks about like this. We represent it by this vector right here. And then the next one that we're going to be using is 13 meters at negative 22.62 degrees. I know to those of you that are more mathematically inclined, this may be an improper angle, but I don't care. And that looks like this. So we've got these two vectors. What do we do to combine them? Well, what we have to do to combine them is we have to perform something known as the tip-to-tail method, which is really we take our two vectors and we put them literally one after the other so that they end up like this. The end result of this is known as the resultant vector. And it's a vector that is created going from the beginning to the end of wherever you start from and ended up at. This is most easily seen with things like displacement, but works equally as well for velocity, acceleration, forces, any other vectors. And so this dashed arrow here represents the resultant vector, the result of our vector combination. So what's the base idea behind combining these things? Well, if we take a look at these 2D vectors, because these are 2D, they only have a rise and a run, we can break them up into their 2D components, their x and y values. How much did they go up? How much did they go over? So if we look at our first vector, the 5 meter long one, we can break that up into its horizontal and its vertical components, seen here as the red and green arrows. We can take the second vector and do the exact same thing and break it up into its horizontal and vertical components. Now, when you look at this, you might notice that, oh, hey, this red here and this red here, they kind of span the entire length of our dashed resultant vector line. And that green and that green, they kind of detract from each other, but they still end up resulting in our resultant vector's drop. So what does that mean? Well, these components actually give the resultants components when we combine them together. So when we have we look at the resultant components, that this dashed red line here represents the horizontal, the x component of the resultant vector, and the vertical one is represented right here. So that's cool. That's how we work it. So mathematically, how do we get to this? So mathematically, what we do is we take a vector and we can break it down into its components by using the sine and cosine functions. Cosine of an angle is defined as an adjacent over the hypotenuse. In other words, it's the x component over the magnitude of our vector. So if we rearrange this to become magnitude times the cosine of the angle, we can get that value. And we can build the vector back up by using our Pythagorean theorem and tangent inverse. So let's see what this looks like with our two vectors. So I build a chart. I like building charts because they help organize all your information. And this chart looks like this. So we're going to have our vector column right here. We're going to have our x components go in the middle column and the y components go in the right column. If you're doing 3D vectors, you can add an extra column onto this. If you're doing multiple extra vectors, not just two vectors, but 3, 4, 20, whatever it is, you can just add more layers along the way. And the very bottom is a section for the resultants values. So what we do is we first put our vectors over here. So we just copy and paste them. When we go to put in our x components and y components, we're going to use that sine and cosine combination. Cosine being the x value, sine giving you the y value. So you're using the exact same numbers in the exact same order, and that's the way that I always remember it so I don't get confused. For cosine, it will just be 5 cosine 53, 13. And for the y component, it's 5 sine 53, 13. Same thing for the 13-meter one. We plug those in. Now, these actually have values. I specifically chose Pythagorean triples so that they came out to being nice numbers. But I don't want you to automatically put the numbers in here because that can lead to rounding and that can lead to us getting inappropriate values. So what I always advise my students doing is when you total these to get you the resultant down the bottom here, you want to just plug everything into your calculator just like this. So you put 5 cosine 53.13 end parentheses plus 13 cosine negative 22.62 degrees end parentheses enter, and that'll give you whatever that is. It'll give you the non-rounded number, and it means you have to do less work because then you're copying down less numbers. So when we do that for our x component and our y component, we end up with a resultant of 15 for our x component because this gave us 3 and this gave us 12. And for our y component, we ended up with a value of negative 1 because this has a value of 4 and this has a value of negative 5. So what do we do with these? These are the components of the result. So we build them back up using our Pythagorean theorem and tangent inverse, otherwise known as the arctangent. So the magnitude for our Pythag, which gives us the third side of that triangle, seeing as how we know two sides of it. We do the square root of the square of these two numbers summed together. So we have the square root of 15 squared plus negative 1 squared gives us approximately, when square rooted, 15.03 meters. So that's our magnitude. That's how much strength our end vector has. And when we go to our arctangent, when we plug this in, we put in tangent inverse of the negative 1 over 15 because it's always rise over run. Then that gives us a value of negative 3.81. I know, again, math people, this is not a proper number. I could add 360 degrees to this in order to make it into a proper number, but we don't need to do that. So when we put that together, we get our resultant vector 15.03 meters at negative 3.81 degrees. Little word of caution before I leave you here for today. If our x component is negative, number one, whenever you have a negative inside your Pythag, always make sure you use parentheses because otherwise you will end up with the wrong answer. But when you go into arctan and you use a negative on the bottom of that fraction, it will automatically put that negative up to the top, which will give you the exact opposite direction of what you need. So what that means for you is that whatever answer you get out from here, if your number going in for your x component was negative, whatever answer you get out, you add 182. So if this was a 1 and negative 15, it would still give me the negative 3.81, but I would have had to add 180 degrees to it, giving us somewhere around 172 degrees. Anyway, that's what it is for today. I hope this was helpful to you, and I will see you next time.